first incredible case of parallel processing unlocking a lot more power. And then, as you said, people begin to use that power across many different industries. The case of the quantum chemistry researcher. When I've heard you tell that story, it's that he was running molecular simulations in a way where it was much faster to run in parallel on NVIDIA GPUs even then than it was to run them on the supercomputer with the CPU that he had been using before.
Yeah, that's true.
So, oh my God, it's revolutionizing all of these other industries as well. It's beginning to change how we see what's possible with computers. And my understanding is that in the early 2000s, you see this and you realize that actually doing that is a little bit difficult because what that researcher had to do is he had to sort of trick the GPUs into thinking that his problem was a graphics problem.
That's exactly right. No, that's very good. Well,
So you
did some research.
So you create a way to make that a lot easier.
That's right.
Specifically, it's a platform called CUDA, which lets programmers tell the GPU what to do using programming languages that they already know, like C. And that's a big deal because it gives way more people easier access to all of this computing power. Could you explain what the vision was that led you to create CUDA?
Partly researchers discovering it, partly internal inspiration, and partly solving a problem. And a lot of interesting ideas come out of that soup. Some of it is aspiration and inspiration. Some of it is just desperation. And so in the case of CUDA, it was very much the same way. And probably the first external ideas of using our GPUs for parallel processing emerged out of some interesting work in medical imaging. A couple of researchers at Mass General were using it to do CT reconstruction. They were using our graphics processors for that reason, and it inspired us. Meanwhile, the problem that we're trying to solve inside our company has to do with the fact that when you're trying to create these virtual worlds for video games, you would like it to be beautiful, but also dynamic. Water should flow like water, and explosions should be like explosions. So there's particle physics you want to do, fluid dynamics you want to do, and that is much harder to do if your pipeline is only able to do computer graphics. And so we have a natural reason to want to do it in the market that we were serving. So researchers were also horsing around with using our GPUs for general purpose acceleration. And so there are multiple factors that were coming together in that soup. When the time came, and we decided to do something proper and create a CUDA as a result of that. Fundamentally, the reason why I was certain that CUDA was going to be successful, and we put the whole company behind it, was because fundamentally our GPU was going to be the highest volume parallel processors built in the world because the market of video games was so large. And so this architecture has a good chance of reaching many people.
It has seemed to me like creating CUDA was this incredibly optimistic, huge if true thing to do, where you were saying, if we create a way for many more people to use much more computing power, they might create incredible things. And then, of course, it came true. They did. In 2012, a group of 3 researchers submits an entry to a famous competition where the goal is to create computer systems that could recognize images and label them with categories. And their entry just crushes the competition. It gets way fewer answers wrong. It was incredible. It blows everyone away. It's called AlexNet, and it's a kind of AI called a neural network. My understanding is one reason it was so good is that they used a huge amount of data to train that system. And they did it on NVIDIA GPUs. All of a sudden, GPUs weren't just a way to make computers faster and more efficient. They're becoming the engines of a whole new way of computing. We're moving from instructing computers with step-by-step directions to training computers to learn by showing them a huge number of examples. This moment in 2012 really kicked off this truly seismic shift that we're all seeing with AI right now. Could you describe what that moment was like from your perspective? And what did you see it would mean for all of our futures?
When you create something new like CUDA, if you build it, they might not come. And that's always the cynic's perspective. However, the optimist perspective would say, but if you don't build it, they can't come. And that's usually how we look at the world. We have to reason about intuitively why this would be very useful. And in fact, in 2012, Ilya Sutskever and Alex Krizhevsky and Jeff Hinton in the University of Toronto, the lab that they were at, they reached out to a GeForce GTX 580 because they learned about CUDA and that CUDA might be able to be used as a parallel processor for training AlexNet. And so our inspiration that GeForce could be the vehicle to bring out this parallel architecture into the world, and that researchers would somehow find it someday was a good strategy. It was a strategy based on hope, but it was also reasoned hope. The thing that really caught our attention was simultaneously we were trying to solve the computer vision problem inside the company, and we were trying to get CUDA to be a good computer vision processor. And we were frustrated by a whole bunch of early developments internally with respect to our computer vision effort and getting CUDA to be able to do it. And all of a sudden, we saw AlexNet, this new algorithm that is completely different than computer vision algorithms before it, take a giant leap in terms of capability for computer vision. And when we saw that, it was partly out of interest, but partly because we were struggling with something ourselves. And so we were highly interested to want to see it work. And so when we looked at AlexNet, we were inspired by that. But the big breakthrough, I would say, is when we saw AlexNet, we asked ourselves, how far can AlexNet go? If it can do this with computer vision, how far can it go? And if it could go to the limits of what we think it could go, the type of problems it could solve, what would it mean for the computer industry, and what would it mean for the computer architecture? And we rightfully reasoned that if machine learning, if these deep learning architecture can scale, the vast majority of machine learning problems could be represented with deep neural networks. And the type of problems we could solve with machine learning is so vast that it has the potential of reshaping the computer industry altogether, and which prompted us to re-engineer the entire computing stack, which is where DGX came from, and this little baby DGX sitting here. All of this came from that observation that we ought to reinvent the entire computing stack layer by layer by layer. Computers, after 65 years since IBM System 360 introduced modern general purpose computing, we've reinvented computing as we know it.
To think about this as a whole story. So parallel processing reinvents modern gaming and revolutionizes an entire industry. Then that way of computing, that parallel processing, begins to be used across different industries. You invest in that by building CUDA. And then CUDA and the use of GPUs allows for a step change in neural networks and machine learning and begins a sort of revolution that we're now seeing only increase in importance today.
All of a sudden, computer vision is solved. All of a sudden, speech recognition is solved. All of a sudden, language understanding is solved. These incredible problems associated with intelligence, one by one by one by one, where we had no solutions for in the past, desperate desire to have solutions for, all of a sudden, one after another gets solved, every couple of years. It's incredible.
Yeah, so you're seeing that in 2012. You're looking ahead and believing that that's the future that you're going to be living in now. And you're making bets that get you there, really big bets that have very high stakes. Mm-hmm. And then my perception as a layperson is that it takes a pretty long time to get there. You make these bets.
10 years.
So my question is, if AlexNet happened in 2012, and this audience is probably seeing and hearing so much more about AI and NVIDIA specifically 10 years later, why did it take a decade? And also, because you had placed those bets, what did the middle of that decade feel like for you?
Well, that's a good question. It probably felt like today. To me, there's always some problem, and then there's some reason to be impatient. There's always some reason to be happy about where you are, and there's always many reasons to carry on. And so I think as I was reflecting a second ago, that sounds like this morning.
Yeah.
And so, but I would say that in all things that we pursue, first you have to have core beliefs. You have to reason from your best principles. and ideally you're reasoning from it from principles of either physics or deep understanding of the industry or deep understanding of the science, wherever you're reasoning from. You reason from first principles, and at some point you have to believe something. And if those principles don't change and the assumptions don't change, then there's no reason to change your core beliefs. And then along the way, there's always some evidence of success and that you're leading in the right direction. And sometimes, you go a long time without evidence of success, and you might have to course correct a little. But the evidence comes, and if you feel like you're going in the right direction, we just keep on going. The question of why did we stay so committed for so long, the answer is actually the opposite. There was no reason to not be committed because we believed it. And I've believed in NVIDIA for 30 plus years, and I'm still here working every single day. And there's no fundamental reason for me to change my belief system. And I fundamentally believe that the work we're doing in revolutionizing computing is as true today, even more true today than it was before. And so we'll stick with it, until otherwise. There's of course very difficult times along the way. When you're investing in something and nobody else believes in it, and it costs a lot of money, and maybe investors or others would rather you just keep the profit or whatever it is, improve the share price or whatever it is. But you have to believe in your future. You have to invest in yourself, and we believed it so deeply that we invested tens of billions of dollars before it really happened. And it was 10 long years, but it was fun along the way.
How would you summarize those core beliefs? What is it that you believe about the way computers should work and what they can do for us that keeps you not only coming through that decade, but also doing what you're doing now, making bets I'm sure you're making for the next few decades?
The first core belief was our first discussion was about accelerated computing, parallel computing versus general purpose computing. We would add two of those processors together and we would do accelerated computing. And I continue to believe that today. The second was the recognition that these deep learning networks, these DNNs that came to the public during 2012, these deep neural networks have the ability to learn patterns and relationships from a whole bunch of different types of data, and that it can learn more and more nuanced features if it could be larger and larger. And it's easier to make them larger and larger, just make them deeper and deeper, or wider and wider. And so the scalability of the architecture is empirically true. The fact that model size and the data size being larger and larger, you can learn more